All right, this is number 7 on the practice exam. So problem 7 asks you to imagine a table. There's friction on the surface of the table. There's a pulley. We have an object sitting on the table. Let's see, the one on the table has a mass of 2 kilograms. So M1 equals 2 kilograms. There is a rope connecting it to a hanging one. The mass of M2 equals, how much was this one? This one is 3 kilograms. And I tell you that this distance, the distance from the floor, is 140 centimeters. Label this as D. And the coefficient of kinetic friction, which you know is 0.4, the friction here. So ultimately, the question we're getting at, the thing we will ultimately find is how long does it take? No, with what velocity? That's right. With what velocity does M2 hit the floor? Question mark. So this is different than any of the other problems we've done, because here we're asking for a velocity. The way we're going to need to do this is to first solve for acceleration, and then use kinematics to relate the acceleration, the distance traveled, and the change in velocity. So our 2 steps here are use the things we've been doing to find the acceleration, and second, use our old kinematics tools to find the final velocity. That's messy. Use kinematics to find V final. So that's where we're headed. To get there, we do the same stuff we've been doing. You know, if it feels like you're doing the same damn problem all over again every time, it is. It's because nature only knows a few tricks, right? F equals ma works for everything. So for object M1, we've got a normal force going up. We've got its weight going down. We've got the tension in the rope going to the right. And we've got friction going to the left. We know the friction goes to the left because this whole thing is going to slide to the right. For the second object, M2, this is much simpler. We've only got one direction to worry about. Its weight goes down, and the tension in the rope goes up. Now, we should pick a coordinate system, so we'll pick that way to be plus x. We'll pick that way to be plus y, since that's what most of you will choose. Although it actually makes the problem a little bit more complicated. So here, in the x direction, I'm just going to copy things off the force diagram. So I have T minus F fric, which I can go ahead and use my eraser and write as mu k times the normal force equals m1 a1x. And then in the y direction, I've got the normal force minus m1g equals m1a1y. And for the hanging thing, I have t minus m2g equals m2a2y. Now, I've got all these acceleration variables. I need to think about what to do with them. So here, a1y is 0, because this doesn't move up and down. And notice that as this one goes to the right in the plus x direction, this one must go down in the minus y direction. So I observe that a2y equals minus a1x. They've got the same magnitude, but opposite signs. So now I just do substitution. So looking at this equation pretty readily, I'll use blue for this. I see that the normal force equals m1g. That shouldn't be a surprise. There's no other forces up or down. It's not accelerating up or down. So now I will substitute this in here. So this equation now becomes, let's see, I've got the tension, but now I know what the normal force is, right? I've got minus mu k mg, which I just found, equals m1 a1x. I forgot my 1 here. That's important. So now I can find the tension and substitute it in here. So I know T equals m1 a1x minus mu k m1g. So now let's take this and put it in for T. So this gives me m1 a1x minus mu k m1g minus m2g equals m2a2y. But notice I've got one equation with my two different a's in. I've got an a1x and an a2y here. And that's, but I know they're related. So I can use this expression to flip the sign of one of those. So that gives me minus m1 a2y minus mu k m1g minus m2g equals m2 a2y. And you know what to do at this point. Move this to the other side, divide by the coefficient. So that gets you that a2y equals minus, whoops, I've made a sign error. Let me write down, yes, and Estef Lebron has pointed out my mistake. Yep. So here, let me write down what I got, and I'll tell you how I know. Well, I'll just tell you how I know here. So this term came from the weight of the hanging thing. Wait, no. How did I figure this out? Oh, yeah. This term came from the weight of the hanging thing, and this term came from the friction of the thing resting on the table. And the friction of the thing resting on the table resists the motion of the thing, but the weight of the hanging thing makes it go faster. So yes, when I solved for the tension, this sign is backwards. Thank you so much. You caught it before I did. That sign is backwards. That means that this sign is backwards, which means that this sign is backwards. Thank you for catching that. There's a joke, don't do math live on Twitch. Well, that's that's what I'm doing. Whenever you do math live on Twitch, you make a mistake. And I certainly did. Anyway, I'm going to take this, I'm going to divide it by m1 plus m2, and this gives me an acceleration of minus m2g plus mu k m1g divided by m1 plus m2. So that's the acceleration of the second object. And we hope that this term is bigger than magnitude than that one. We've kind of been given that this is heavy enough to pull the whole thing off. So let's put in numbers. We know numbers for this whole thing. We can actually probably don't need to resort to Google Calculator for this. So minus m2g is going to be minus 30 newtons. We're using 10 for g. Mu k is 0.4. m1g is going to be 20 newtons times 0.4 is 8 newtons over 5 kilograms. So that's 38 newtons divided by 5 kilograms. Let's see. So 38 divided by 5 is going to be the same as 76 divided by 10. So this gives me that doesn't seem right. Let me ponder. No, that's right. No, of course not. It's not 38. It's 22, right? This is minus 22 newtons over 5 kilograms is minus 4.4 meters per second squared. I am tired, y'all. So that's the acceleration, is minus 4.4 meters per second squared. Makes sense. You expect this to fall, but less than g. Yeah, Denara, I definitely messed that up. So this is the acceleration. It's less than g. It's less than half g. You might imagine if there is no friction here, then I would get 3/5 g, because I've got 5 kilograms I must move, but only 3 kilograms contribute to its falling. So I'd get 3/5 g if there's no friction. This is the minus 30 over 5. But because there's friction, the magnitude is less. So now, we've done this bit. Now we need to do the kinematics. There's two ways to do the kinematics. One of them involves the use of something that we derived called the third kinematics relation, which is the one that doesn't have time in it. So we saw that this was for your second homework, third homework, second homework. No, this was Friday's recitation after the first quiz. It was different this year. We derived this formula. So here I know the initial velocity, I know the acceleration, and I know the distance traveled, which is d. This will let me find Vf. So I know Vf squared minus 0 equals twice the acceleration times the distance moved. Now, the distance moved is downward. So, right, because we are traveling down in this problem. So I have Vf squared equals 2 times minus 4.4 meters per second squared the distance traveled is minus 1.4 meter. So VF is going to be the square root of all of that. I don't feel like doing that in my head. So we're going to ask the calculator to do that one for us. So, dear Google Calculator, I want to know the square root of 2 times 4.4 meters per second squared times 1.4 meters. Google Calculator thinks about it a bit and says that this is 3.51 meters per second. And the velocity is downward. If you didn't remember this kinematics relation, then instead of doing that, you can, you know the acceleration. So you can use that in the position equation to find time, and then substitute that into the velocity equation to find final velocity. So that's the other way to do it. Any questions about this one? So this was kind of a two-step thing. We wanted to know the final velocity here. So this tells us, hey, I need kinematics. I can't just do it with Newton's laws. So see you again for the last one.